we're going to start working with little cases and go through the basics of simulation with this small case. As I talked about, the basics of doing a run are really straightforward, particularly if you're using a PWB file. The PWB file will store everything associated with a particular run, all the options, what you want to save, store. We'll talk about plotting definitions. So you pretty much, if you've got a case, you can open it up and run it. And that's what we're going to do right now. So why don't you go and open up case example 13.4. You don't have to save anything. Example 13.4. If you're wondering how come this is called example 13.4, this is from my book. Transient stability used to be covered in chapter 13, and this is the fourth example from chapter 13 of the book. Since then, we've moved transient stability to chapter 11, so this is really now example 11.4, but the name persists. This is a simple case. We just have a generator connected to something called an infinite bus. Infinite buses don't exist. They're something that usually you just run into in an academic setting, but because PowerWorld Transient Stability got its start as an academic tool, PowerWorld does directly support infinite buses. So in this example, we're assuming this bus is an infinite bus. All that means is that its voltage, magnitude, and frequency are held constant. This is actually a useful concept that we'll cover later on when we talk about play-in models, which are used for PMU validation studies, because play-in models allow you to have an infinite bus where it's assumed it's such a large generator, nothing that occurs out here affects that generator, but rather than keeping it constant like we will do in this example, with a play-in model, you can play in how the generator actually responded during a disturbance from recorded data, and its frequency and voltage will vary as it actually did. And we'll get to that later on. For this example, this is a fixed bus. That means the frequency, because this large generator is a fixed 60 hertz frequency, this is going to stay at 60 hertz, except this generator will be oscillating around that. So go ahead and run it. And to run it, all you do is add-ons, transient stability. So you open up the transient stability display. And we do have a predefined contingency here. At 1 second, we're going to put a fault on bus 3. Then we're going to clear that fault by opening the 2 lines incident into bus 3. And on the question of time in cycles and time in seconds, in talking with Caroline, so just hit run transient stability, and you'll do the run. And in this case, a plot automatically displays. And we'll talk about how plots are generated later on. But this is demonstrating the capability that a plot can show different types of data on it. Here in the blue, I'm showing the rotor angle on the generator. Here in the black, I'm showing the per unit bus voltage for bus 1. Okay, so if you want to change parameters associated with your generator, you can go to the one-line diagram. So I just kind of moved the transient stability display out of the way. So here I put transient stability, I just kind of moved it out of the way to get access to the one-line diagram. I right-click on the generator. I can play around with the parameters like stability. I get access to this. If you want to run that same fault, let's say you want to make your H really big. H is the inertia on the machine. So say you want to make it 100. All you got to do is enter in 100 here. Pick whatever value you want. Go to the transient stability. Run the case. and now you get a vastly different response because you've changed the parameters on your system.
You don't have to reset any kind of a reference state then with this tool? It's automatically any change?
No, because what happens when the way the transient stability code is actually written is you can think about simulator as over here. Then we have a separate transient stability engine over here. You don't see that here, but that's what's going on. So when you click run, what it does is it saves a copy of what you've got in the power world side of things, what we call the power flow side. It saves that. That's your saved case. Then it packages up a bunch of numerical values in a binary stream, transfers it over to the transient stability engine, runs it, and then transfers the data back over to the power flow side. So we'll talk about being able to pause a simulation at any point in time and look at the results. Your initial case is still stuck over here. So when you restore it, it's automatically restored. So if you hit run again, it's going to grab that copy, put it back in there. You've changed parameters around, run it, and so the short answer is no, you don't have to do anything.
Oh.
Yeah, I mean, the idea is to make it as simple as possible for you to get access to stuff and change things around. So the slides go through the dialogue that I talked about. You can change parameters around. The main transient stability form here, if you want to change your contingency, like let's say I want to change this from clearing at 1.34 seconds, I'm going to change it so it clears at 1.1 second. You can just enter 1.1 in there, 1.1 in the next one. Values can be anything you want. Then you run it, and you see the response. The only difference on this one is I changed that H to 100. If I wanted to keep that change, fine. If I want to put it back to where it was, I either have to reload the case in or change it back. Okay. So I'll just change it back here. Original. Okay, we're back on the slides here. There's various displays here that let you customize a lot of things, and we're going to go through the details on that. Playing around is always encouraged, so you can take a little case and play around with it, but some of that we're going to cover in the training. Simulation is the main page. That's one right here, and we'll be covering that right now. Then we'll go through the options in the next one and get through all this, including the transient limit monitors, which are a whole section. This is the simulated event listing there. That lists the events that go into defining the contingency. If you right-click on that, you get a dialog that shows how that's defined. Here is the starting time, which is practically always 0. The ending time, 10 seconds, 100 seconds, whatever you want to run. Time step right there. Let's see, we covered that. We're going to get to the ability to use different contingencies, because a lot of times you don't just want to run one contingency. You might want to have different contingencies defined. So we'll talk about this later on. This allows you to set up a whole group of contingencies. Then we have options that let you run a whole bunch simultaneously and compare results on them. That'll cover later on. Here's the fault definitions. On this side, just briefly, simulation is the main page we talked about. Options we're going to get to. Result storage, we're going to have a little bit more detail there, but that specifies how you store the results. Plots lets you define the plots, which we'll talk about. Results is where you can see the numerical results. We'll talk later on about single machine infinite bus eigenvalue analysis. Validation is the first section after lunch. Then if you want to step by step through a contingency we let you do manual control on the process as well. And then transient limit monitors are covered later on. Okay, options in general. We have a number of different options here. So let's go to the options page. So if you click here on options and then go to the general one, this provides you with some general options for how the system responds. A lot of this here is MVA base for input display of generator values. Practically always you want to use the individual generator MVA base. We in North America display stuff on generator MVA bases. In China, it turns out they tend to use a common power flow MVA base. So that's the reason why that's there. So you would not change that. I don't think I've ever changed that button in the whole time that I do this. This here is talking about options for how data is transferred between the running simulation and what we call the power flow side. The simulation, remember I talked about the power flows here, then there's the separate transient stability application. It's run in the simulation. Every once in a while, we want to get data back from that simulation to interact with it. If you're running in kind of a batch mode, you really don't want to be doing that too often because it slows down performance. This is less of an important issue for a large case because most of the time is spent in the simulation. There is some time that's associated with moving data back over the power flow to display it. If you don't care about that, normally you don't go in and have to mess with these options. Mostly those options are there for the use of it in an educational sense. One exception, though, is if you want to do a manual control on the simulation, there are options here that say, if I'm manually running through a simulation, transfer results to power flow on a manual time step, as you step through the simulation manually, usually this occurs automatically, you can transfer the results back over and see them on the power flow side, which includes on the one-line diagram. So let's go ahead and just play with that on this example here. So I want you to go to the states manual control, which is right here, states manual control. So it's below plots, below results to RAM, transient limit monitor, states manual control. This allows you to manually go through this simulation. So we saw the result of this simulation. Okay, we just ran it, you saw the plots. Let's say you want to dig in and figure out what's going on. So we're going to, first of all, let's click Reset to Start Time. That takes the simulation back to the start of it. This provides all the gory details about the states in your simulation. In a WECC case, you would have 100,000 states potentially. There's very good sorting here that lets you get access to them. This case is just a very small case. Most of you might know about angle and speed, all this other stuff, unless you've done transient stability runs you don't care about. But if you're trying to debug a case, this is really useful. So let's say I want to do a specified number of time steps. Just click on that. By default, it's 1. That moves the case forward 1 time step. So we're now moving forward in time 1 time step. And as it does that, the option we've got set is actually transferring all this data over to the power flow side. So you can see on the one-line diagram what the system looks like at time 0.008 seconds. And we actually have fields that you can put on here that on the one line show you the time. If you look at the case information display, it would show you the network, buses. That's the state of your case at this time. And we put a yellow background on here because we wanted people to realize you're not looking at the power flow, you're looking at a pause contingency or pause transient stability case. Well, on this example, nothing interesting occurs until time t equals 1. So if we go back to the transient stability page, I'm paused at time t equals 0.008. If you don't have to do this, but let me just make sure. Okay, the fault occurs at time t equals 1. So on this manual control page, we're going to say to it, run until time t equals 1. So in this field right here, put a 1 in there and then click until run until specified time t equals 1. Okay. If you look at the states when time t is equal to 1, nothing has changed. That's because we have to speak time t equals 1. Is it a little before 1 or a little after 1? That event's going to occur right at 1. This is right before 1. Now do a single time step. Just do specified number time step, do 1, 0.08. Now stuff is changing. If you look at that one-line diagram, that is representing your fault-on case. Our contingency was a fault at bus 3. Bus 3's voltage is now 0 per unit. That is a pause during the event. If you want to click another time step forward, go ahead, or just do number of time steps. Now we're seeing what's happening while the fault is on the system. And we clear the fault, I think at 0.11 seconds. So you can either run until 1.11 or you can manually time step to get to that. But this is showing you the details on what's going on. And you can look at this state with all the Power World displays, like the case info, network, buses display. That gives you a lot of power when you're dealing with detailed study. What's going on with this case? Very useful to get a lot of insight. And when we debug cases, we do this all the time. Okay, so then you can click on through, and now you see the response was the opening of those lines. Now this is dead, and you're watching how things iterate around. So you might think, well, wouldn't it be kind of fun to just run this thing and see it animating? That's where those options I talked about before come in. If you go back to the options page, this option here says update displays after interval check. That updates the transient stability display. This one transfers the results to the power flow after interval check. This is saying how often should I transfer the results over to the power flow side. Check both of those. Okay. And then you can either continue where you're at, you're paused right now, you can continue to run, or you can abort and you can restart. I'll just continue to run. Now you'll see it oscillating kind of back and forth as it's running through the study. So to get it, I had to check those two boxes there. Okay, I had to check update displays after interval check and then transfer results. This bot, or this one here, run at a rate proportional to real time. If you're thinking, wow, this would be really cool, I'd like to show this in my class, or I'm going to do a presentation of someone, I want to show a visualization of what's going on, but I want to kind of control how fast it runs. If you check that one, run at proportional to real time, and the slowdown here is 5, now what I'm going to do is I'm going to rerun my simulation. If I had put a time display on here, you could see the time as it's going, but you'll be able to see it here. if you click Run Transient Stability now, it's going to run through the transient stability, transferring the results over here, but at a rate that's 1 second goes by in 5 seconds. So now I could be talking about it in class. I could say there's going to be an event right now, and now you can see the generator rotor changing, and it's oscillating back and forth, and the flows are changing, and things like that. Okay, so it's more a visualization teaching tool. The time stepping through is quite useful, but these options here are not commonly used in actual studies.
And for the users here, in general, there's not going to be the debugging going on?
Well, it'd be case debugging. I don't mean, see, when we get a case, like we'll get a WCC case that somebody might say, maybe it's Gordon says, hey, there's some problem with this case. We look and see what is the problem with the case. And we look at, is it a Power World bug, heaven forbid? Is it model parameter? Is it something else? So you might be, I don't know how much you guys would do it, but somebody's doing it where they're looking at a WCC case and saying, how come this isn't working right? That you guys?
Well, in theory, it shouldn't be.
Yeah.
It should be, the case should be good. It's approved for production use, but then as you use it, then you do find problems. But in general, I think the operational cases
are good.
They're getting used. The showstopper data problems are pretty much corrected, thanks to the autocorrect stuff too. And so then they're more into production mode and trying to find limits rather than digging into the interesting stuff there.
Yeah, and we're almost finished with this section, but as we do this, Power World transient stability can have different faces to different users. Some people want to dig deep and find out what's going on. Others just want to do a run, or they might want to do 500 runs. And we support both and have tools available for both, because the needs of one user could be quite different than the needs of another user. Yeah, so we're on slide 20 right now. 20 is going back to the options page. So if you go back to transient stability options, we covered the general options. The only other one on the general options is, how do you want to identify buses and events and results? Do you want to call them by their name, by their number, by their name with the number in parentheses, number or name in parentheses? That allows you to get access to data that has the name the way you want it to be shown. Usually I use number with name in parentheses, but others want to go the other way. The other one that we're covering here is the second page on options, power system model, and that gives a number of different options associated with how the power flow is actually modeled. You wouldn't change the nominal frequency, that's 60. You wouldn't change the MVA base, usually that's 100. Network solution tolerance, that's similar to the power flow solution tolerance, typically 0.1 MVA. Various values associated with solving the network equations. Usually that's not something that you have to get into. Hopefully they're well-tuned cases that they don't have to get into it. Infinite bus modeling. This one, model the power flow slack buses, infinite buses. That would only be set for an academic case. You would want no infinite bus modeling, and that would be the default. This one's important, handling of initial limit violations. We talked about what happens if you've got an initial limit violation. What do you want the software to do? The default is to modify the limits and run. So if a limit on a VR on an exciter is 10 and the VR initializes to 15, by default we will say, hey, the limit really should be 15, and we'll run. If you want to abort and go fix that limit, wonderful. Click abort. If you want to run without changing the limits, you're not going to start out flat. You're going to see initial oscillations because the power flow and transient stability models are not matching that. So that's provided as an option. One that would be always checked for you guys is include dynamics of the Pacific DC intertie if appropriate MTDC records exist. Obviously, that's got a limited market for that, but it's a big market, WCC. Bus frequency measurement time constant, you might not realize it, but when we show you the bus frequency is not a state variable. It's actually picked up by looking at how the angles change and then sort of taking the difference in how the angles change. We use a first-order lag model. The time constant there on that first-order lag model is important. This is not really talked about, but when you bring models into stabilizers, the value here is important. PSLF has a value, and that's what we've got that set to, is what PSLF has. Okay. Is that a real value? No, it's not a real value. It's a fake value, but it does have an impact. How do we want us to model the load? Usually the load has a model associated with it, but if you don't give us a model for the load, we have to make up something. This is the load model of last resort. And by default, it's constant impedance.
Oh, this used to not be on this page. I don't remember this. The constant power loads at 0.7
Yeah.
voltage sensitive. So this must be in response to the failed network equations for at Centralia. It was the older or the previous load model. There was a large constant power component for the station service load, and so then it would just stop. And so I think then this was apparently the fix for that. You know.
Right. What this is associated with is when you do a power flow, usually in the power flow you have a constant power load. Load is not really constant power because that will break down as the voltage gets too low. Okay. So where does it break down? These parameters specify where do those models break down, and they're brought over from the power flow. At 0.7 volts, the assumption is constant power models start to gradually become constant impedance models. And constant current models that when the voltage goes below 0.5 gradually become constant impedance models.
Yeah, so this is new because you had to check something in order to have it follow this. The way I'm interpreting this now is it's going to follow it even for the composite load model, which has a small, for static loads, often a small constant MVA component, and so I think we want a choice whether to have this applied or not. And the way I interpret this is we don't have a choice. We have to specify a voltage sensitive threshold for the constant MVA model.
Unless you put zero, then it goes.
Unless you put zero.
Yeah, I mean, you can change these values. The problem is we're trying to prevent people from having a problem where normally it won't occur, but if you put a fault on a bus that's got a constant power model in it, what do you want us to do when you're saying my load is 100 megawatts and my voltage is 0? What do you want?
Yeah. So I think then going forward, then this would be a change for users like me to pay attention to this and put zeros when we're using a composite load model.
Well, I don't know that you want that in the composite load model. Jamie will be talking about that on Thursday. We have done a lot of benchmarking on the composite load model, which we haven't covered yet, so we'll get to that on Thursday. The last ones here, normally you don't have to worry about. The defaults are fine. Ignore speed effects in the generator swing equation. That would be unchecked in a real study. It's only something that occurs in small academic systems. Fast valving is something that there's options associated with it. The ones over here have to do with, mostly this is differences between PSSE and PSLF.
What's the function of the change button? It seems to go to the distributed computing list in here.
Change does? That's a feature. Write that one down.
Yeah.
I don't know. I would think I could just enter it here. I guess it set it to 0. Maybe that was a feature for you, Gordon, if you try to change
You know
it.
what? That's supposed to go, it's actually probably, it's probably the same values as that are on the power flow.
Right.
There's not two separate sets of those. So it's supposed to go to the common options tab instead of that tab. That's why it's going there.
So then if it's changed here, it's gonna be reflected in the power flow.
Right.
As 0 if I change it 0 here.
Right.
So that's where you would have to change it, is in the common options on the distributed computing.
Well, no, it has nothing to do with the distributed computing. It's supposed to take you, it's supposed to, when you click that change button, it's supposed to take you to a different tab.
Yes.
Which tab? Yeah, it's a bug. We'll get that fixed.
It's taking you to the simulator options dialog, and it'll take you to the power flow.
Oh, it's going to take you. This is an option in the power flow. Yeah, it took it to the wrong option.
Yeah, it should take you
This is. I went over to the power flow. This is coming off of an option on the power flow. That's where that's coming from. These options here on kind of the far side, you normally would not have to deal with these options. These options are set based on what type of file you loaded in. If you loaded in a DYD file, they're set one way. If you loaded in a DYR file, which you would be less likely to do, they're set another way. This is just differences in how PSSE and PSLF handle various situations. And normally, they're not that important, but as I said, this stuff has been extensively validated, and we'll run into situations where, you know, the exciter saturation function varies between the two. The exciter automatic parameters, which are details that you don't have to worry about too much, they vary. The machine saturation, what if S12 is less than S10? One package ignores them, the other one flips the values. You can do it either way, and if you're running one and you say, hey, how come Power World's not matching? And we say, well, we flip the values, whereas they treat them as 0, we put an option in that's set based on where it came from. What do you do if saturation when one SE value is 0? You know, how do you treat this curve here if one value is 0? One package treats it as always 0, which I think if I put in a point here and a point somewhere else, that you want a curve fit a quadratic through those points. I don't think you want to treat it as 0. Okay? But reasonable people can differ on that interpretation. And if your software package treats it as 0 and you're like, hey, how come Power World's not matching? And by default, you assume your software, let's say you're running PSSE and you've used it forever, and Power World comes out and gets a different result, who are you going to think is right? Probably not Power World, because they're the new player on the block. We know why the difference is. It's because of how the difference between what PSLF is doing and what PSSE is doing, and we handle that. Including GIC effects is something that's new that I'll show you kind of a simulation of that later on. Integration method, usually use second order Runge-Kutta. This is include undocumented governor PI limits. That's something that was addressed by WECC because of the results of the project we're doing with Terry, where we saw that what some packages were doing was correct but undocumented. Other packages were incorrect but correctly documented that they were doing it incorrectly. So we included an option that is by default true.